Three-phase AC induction motors use magnetic induction to convert three-phase AC power into mechanical energy. They're used throughout industry to drive equipment such as pumps, compressors, and fans. Three-phase AC induction motors are economical, efficient, and reliable, but even the best equipment may still break down. Since your job includes maintaining three-phase motors, you need to be thoroughly familiar with these types of motors. In order to understand how a three-phase AC induction motor works, you first need to understand the basic principles of alternating current and three-phase AC. So far, we've been looking at single-phase alternating current. Three-phase alternating current is actually three separate alternating currents. The three currents are very similar, but they're produced at intervals. In other words, they're out of phase. Each of the three phases flows through a separate conductor. In reality, all three currents are generated at once, but we'll look at them individually to get a better idea of what's going on. In this part, we'll identify the parts of a typical three-phase AC motor, and we'll look at two common types of these motors. We'll also see how a three-phase AC motor operates. When three-phase alternating current flows through each coil pair, a magnetic field is produced between the coils. The strength of this magnetic field changes as the current increases and decreases, and the magnetic field's north and south poles reverse when the current changes direction. We can use the stator illustration to see how the magnetic field is generated and how it rotates. In this example, we'll use colors to represent the magnetic field. Green is north and yellow is south. We'll also slow the speed of the rotation down to better show what it looks like. When the first coil pair is energized, current flows through it. This current produces a magnetic field between the coils. The magnetic field changes with the current, and its north and south poles reverse with the changes in current direction. The same is true for the second coil pair and the third coil pair. As current flows through each coil pair, the strength of each magnetic field produced changes as current increases and decreases. The north and south poles reverse when current changes direction. The magnetic fields produced by the three sets of coils merge to form one overall magnetic field. For example, this is a representation of the polarity of the overall magnetic field between the stator coils when the first phase current is at its maximum. This is the polarity of the overall field between the stator coils when the second phase current is at its maximum. And this is the polarity of the field when the third phase is at its maximum. The net effect, through the complete three-phase cycle, is that the overall magnetic field between the stator coils rotates. The speed at which the magnetic field rotates depends primarily on two factors. One factor is the frequency of the current, that is, how many times the current cycles each second. The greater the number of poles in a stator, the slower the rotation of the stator's magnetic field. And the slower the rotation of the magnetic field, the slower the rotation of the rotor. So, a motor may be selected to drive a particular load based on how many stator poles the motor has and how fast the load needs to rotate. Now that we've looked at the magnetic field produced in the stator of a three-phase motor, let's see how this brings about the rotor's rotation. Whenever there is a relative motion between a conductor and a magnetic field, a voltage is induced in the conductor. Here's the rotor of a three-phase motor in the rotating magnetic field of the motor's stator. The rotor contains conductors, so the relative motion between the rotor and the stator's rotating magnetic field induces a voltage. The induced voltage creates a flow of alternating current in the rotor's conductors. So as the stator's magnetic field rotates, the current flowing in the rotor produces a magnetic field that expands and collapses as the current in the rotor alternates. The rotor's magnetic field interacts with the stator's magnetic field, causing the rotor to turn in the same direction as the rotating stator field. There is also relative motion between the rotor's magnetic field and the stator's coils. As a result of this relative motion, the rotor induces a voltage in the stator. This voltage increases what is called the effective voltage in the stator. Effective voltage is the voltage that actually exists in the stator at any given time. The three voltages combine into a single effective voltage that causes current to flow in the stator. The three individual voltages are important because a change in any one of them causes a change in the effective voltage. The effective voltage in the stator of a three-phase motor is greatest when the motor is first started. When the motor is first started, the stator's magnetic field is rotating at a high speed, but the rotor is just beginning to turn. The difference between the speed of the rotor and the speed of the stator's magnetic field is maximum. That causes the rotor's magnetic field to change rapidly. The faster the rotor's field changes, the greater the voltage induced back into the stator. Therefore, the voltage induced in the stator by the rotor is at its maximum when the motor is started. This makes the effective voltage high when the motor is started and results in a high starting current. If an ammeter is connected to the motor, we can see the high starting current when the motor is first started. As the difference between the speed of the rotor and the speed of the stator's magnetic field gets smaller, less voltage is induced in the stator. So, the effective voltage decreases and current decreases. Now, there is always some opposition to the rotor's rotation. It usually comes from friction within the motor, the load the motor is driving, or both. This opposition causes the rotor to turn more slowly than the stator's magnetic field, so that the rotor's rotation never reaches the exact speed of the rotation of the stator's magnetic field. This means that there is always some relative motion between the rotor and the stator's magnetic field. The speed of the stator's magnetic field and the speed of the rotor are related, even though they're not equal. If the speed of the stator's magnetic field is cut in half, the rotor's rotation slows by approximately half too. The difference between the speed of the stator's magnetic field and the speed of the rotor is called slip. Slip is often expressed as a percentage. The amount of slip found in various induction motors varies, from approximately 5% to about 13% slip depending on the motor. This means that the operating speed of the rotor is about 10% slower than the speed of the stator's magnetic field. Slip also determines the amount of voltage induced in the stator by the rotor. The greater the slip, the greater the effective voltage in the stator, and the greater the amount of current in the stator. For example, when an increased load is placed on a motor, the rotor slows down. When slip increases, more voltage is induced in the rotor by the stator's magnetic field, and the current flow in the rotor increases. Because of this increase in current flow, the rotor's magnetic field gets stronger. The rotor turns more strongly, and the motor produces more mechanical power. At the same time, the effective voltage in the stator increases. This increase in voltage causes current to increase, and the electrical power that the motor is using also increases. In this part, we'll look at how the speed of an AC motor can be controlled. One way speed control can be provided is by using sophisticated electronic devices and specially built motors. Another way to provide speed control is to construct motors with more stator circuits, each with different numbers of poles. The speed of the motor's rotation is determined by how many poles are in the circuit that's energized. When a motor is well cared for, many major problems can be avoided. Certain routine measures can be taken and maintenance performed to keep problems from occurring and to ensure a motor's continued performance. Motor inspections are done to detect minor problems before they become major. This part of the program looks at how operating and non-operating three-phase AC motors can be inspected. Before inspecting a motor that's operating, you need to take safety precautions, such as putting on any required personal protective equipment. The inspection begins with a visual inspection for any loose or broken parts. The motor's air vents should be checked for dirt, grease, and other obstructions to airflow. This airflow through the motor provides cooling for its internal parts. Also, listen to the motor. A motor that's operating correctly should have a smooth, steady sound. An unsteady sound or an increase in motor noise could be an indication of motor trouble, such as an electrical fault or a bearing failure. Unusual movement of the shaft or vibration of the motor can also be an indication of motor trouble. Unusual movement of the shaft or vibration of the motor could be caused by shaft misalignment, an unbalanced load, or worn bearings. Vibration can be felt as well as heard. so it's a good idea to touch the motor carefully to locate the area of greatest vibration. First, to help make sure you won't be shocked, make sure the motor's grounding strap is attached before you touch the motor. You must use extreme caution when touching the bearing housings. If there's a problem in this area, there may be enough heat to burn you. Some motors have instruments installed in them to measure temperature and vibration. For other motors, you may need to use a vibration meter to measure the motor's vibration, and a contact pyrometer to measure its temperature. Regardless of the instruments that are used, the readings you take should be compared to previous readings taken under the same conditions to see if a trend is developing. A trend toward increasing temperature or vibration, or both, may be a sign of a problem that will cause a motor failure in the future. A trend of increasing readings should be reported to a supervisor. If the motor you're inspecting is a wound rotor motor, pay special attention to the slip rings, the brushes, and the brush rigging. All of the brushes should be touching their slip rings. Brushes that are worn can be replaced after the motor has been stopped and locked out according to approved procedures. The current flowing to an operating motor should be checked for balance between phases. A balance between the phases means that the current in each phase is the same. If the phases are not balanced, the motor will not run efficiently and could become mechanically unbalanced. Some large motors have built-in ammeters. If the motor you're inspecting does not, this check can be made at the Motor Control Center. Access to the motor line leads and controls is attained by unfastening the front of the control center's enclosure. These three conductors supply the motor's power. A clamp-on ammeter can be used to check the current flow in each of the three conductors. If the three-phase currents are not the same, there is a phase imbalance. A phase imbalance can be caused by a variety of problems, such as grounds, shorts, or mechanical misalignment. If there is a phase imbalance, a supervisor should be informed. Now let's look at how a three-phase AC motor that is not operating can be inspected. To make sure that the motor is not accidentally started while it's being inspected, the motor should be locked out and tagged according to approved procedures. For many motors, particularly ones that are exposed to the elements, a heater is used to keep them dry while they're shut down. When a stop motor is checked, it's a good idea to check any heaters to make sure they're operating properly. Sometimes there will be an indicating light in the heater circuit to show that the heater is energized. The heater can be checked to make sure it's energized by measuring the current flow through it with an ammeter. You can begin your inspection of the motor with a visual check for any signs of trouble. The entire motor should be checked for signs of dampness. The bearing housing should be checked to make sure there is no leaking grease or oil. The stator windings can usually be seen through the ventilation slots at the end of the motor. You should look for discoloration of the motor's insulation, signs of burnt insulation, and dirt. If the motor has a wound rotor, the brushes and the brush rigging should be checked for signs of trouble such as broken brushes or loose parts. The surfaces of the slip ring should be checked for discoloration or grooving, and any signs of trouble should be reported to a supervisor. In order for a motor to operate correctly, the rotor must be centered in the stator. Once in a while, you may be asked to check the air gap between the rotor and stator of a non-operating motor to make sure that the rotor is centered correctly. In this case, part of an end bell is removed. The space between the exposed part of the rotor and the stator is checked. To check the spacing at the bottom, a reading is taken by inserting a feeler gauge through slots so that it's between the rotor and the stator. The readings should all be the same. If they're not, it means that the rotor is not centered, and you should report the problem to make sure that it's taken care of. Perhaps the most common maintenance test for a three-phase AC motor is an insulation test. This test is performed on non-operating motors to find out if motor insulation has failed or if it's deteriorating. For this test, a high-range ohm meter called a meg ohm meter is used. Meg ohm meters are available in several varieties. Some are powered by a hand-cranked generator, and others are line-powered. Before an insulation test, the motor is stopped, locked out, and tagged according to approved procedures. The motor is isolated from its power source by disconnecting it at the motor starter or at the connection point at the motor. After the motor leads are disconnected, they're clipped together. The next step is to test the meg-ohmmeter and its ground connection. First, the meg-ohmmeter is operated to see if it will indicate infinite resistance. Then the motor leads are connected together to see if the meter will indicate zero resistance. Next, the meg-ohmmeter's ground lead is connected to ground. The ground connection is tested by connecting the meg-ohmmeter's line lead to ground at another location. The meter should then indicate zero resistance. The meg-ohmmeter's line lead is then connected to the motor leads, and the meg-ohmmeter is operated to perform the test. Typically, the length of the test is 1 minute, but it can be longer. Check with your supervisor to make sure that the proper time is used. In this case, the reading on the meg-ohmmeter is nearly infinity. In general, the reading obtained from this test should be at least 1 megohm for each 1,000 rated volts, with a minimum of 1 megohm. If the reading is not at least 1 megohm for each 1,000 rated volts, the motor has at least a partial ground. The reading should be compared to previous readings to see if a trend is developing. This comparison is a good way to detect deteriorating insulation before it fails. If the reading is not acceptable, approved procedure should be followed to report it. During the test, the motor receives a charge from the meg-ohmmeter that must be discharged after the insulation test. This meg-ohmmeter has a discharge position on its selector switch. With the switch in the discharge position, the motor is discharged for approximately 4 times the length of the insulation test. If there are no problems, the motor's leads can be reconnected after the motor has been discharged, and the motor can be returned to service. In general, most electrical problems in 3-phase AC motors occur in the stator. In this part, we'll look at 3 common types of faults to look for in a motor's stator: grounds, opens, and shorts. When there's a ground in the stator, there is low resistance through the insulation between the stator coils and the motor frame. A high-range ohmmeter, called a meg-ohmmeter, can be used to test for grounds. First, the meg-ohmmeter is tested to ensure it's working properly. The meg-ohmmeter's ground lead is then connected to the motor frame, and the other lead is connected to the stator. The meg-ohmmeter is then operated to perform the test. If no ground is present, the meter will indicate infinite resistance. If a ground is present in the stator, the meg-ohmmeter reading is lower than normal, maybe even 0. If a ground is found, the next step is to find out what is causing it. Grounds can be caused by chafing of the motor leads against the motor's frame. This problem may be corrected by re-insulating the leads. If the motor is an unsealed motor, moisture may be the cause of the ground. In this case, the stator should be inspected visually to see if there are any signs of moisture. If the ground is caused by moisture, the problem may be corrected by drying the motor. There are many ways to dry a motor. One typical method is to use a heat lamp. If the ground is inside of the motor and drying the motor doesn't solve the problem, the motor will usually be sent to a motor shop to correct the problem. An open in the stator is a break in a stator coil that interrupts or opens the current path. There are 2 general ways to test for opens in the stator of a 3-phase AC motor. The method you use is determined by the way the motor's stator coils are connected. The stator coils can be connected in either of 2 ways, in a Y connection or in a delta connection. One way you can usually determine how a motor's stator coils are connected is to check the motor's nameplate. If the nameplate doesn't include this information, check the motor manufacturer's manual. The stators of both Y-connected and delta-connected motors can be tested for opens by using an ohmmeter or a multimeter. With either of these devices, a resistance reading is taken for each current path. Now that we've seen what's involved in the test, let's look at an example in which a multimeter is used to make resistance readings. The only way to find out which circuit an open is in is to take a reading for every one of the current paths. When this test is performed, the 3 motor leads should be marked according to their phases to identify them. In our example, we'll use stickers with letters on them to ID each lead. We'll use the letter A to identify the first phase lead, the letter B for the second phase lead, and C for the third phase lead. The multimeter is set for resistance, and it's connected to lead 1, which is identified with the letter A. and lead 2, which is marked with the letter B. The multimeter shows an infinite resistance reading between these two leads. Next, a reading is taken between lead 1 and lead 3, and the multimeter indicates that there is infinite resistance between these two leads. From the readings that have been taken, it's evident that there's a break in the current path between lead 1 and lead 2, and between lead 1 and lead 3. So it seems likely that the open is in the stator's first coil. The next step, then, is to make sure where the open is. You can make sure where the open is by taking a reading between lead 2 and lead 3. The multimeter indicates normal resistance between these two leads. Since this current path would not have a normal resistance if there were an open between lead 2 and lead 3, the open must be in the first coil. Now, in a delta wound motor, you always get continuity, that is, an uninterrupted connection, between any two leads, even if there's an open in one of the coils. Now let's see how a delta-connected motor can be tested for an open with a multimeter. After the leads are marked to identify them, in this case with colored tape, the multimeter is connected to lead 1 and lead 2, and a reading is taken. The reading is written down for later reference. Next, a reading is taken between lead 1 and lead 3, and again the reading is written down. At this point, it can be seen that there is a big difference between the two readings. The resistance is a lot higher between lead 1 and lead 2 than it is between leads 1 and 3. This means that the open may be in coil 1 or coil 2. A reading is taken between leads 3 and 2 and written down. This reading is about the same as the reading for leads 1 and 3, and it's about half the reading for leads 1 and 2. Therefore, the open is between leads 1 and 2. Now suppose you check a motor's nameplate and it doesn't show what kind of connection the motor has, and you don't have the manufacturer's manual. In this situation, the motor should be tested as if it's delta connected. If the test is made for balanced resistances rather than just for continuity, it is possible to determine the location of an open regardless of the motor type. In any case, when an open is detected, it's usually necessary to rewind the motor. The last stator test we'll look at is for shorts. A short is an accidental current path of low resistance. When a short occurs, a conducting path interferes with one of the normal current paths. The current takes the path of least resistance, which is through the short's interfering conducting path. A short can sometimes be detected by testing for a balance of resistances in the current paths. For example, a partial short in the stator windings can result in a phase imbalance. However, when there is a short in the stator, the imbalance in the current paths may be too minor to register on a multimeter. Since it may be difficult to locate a short, it's a good idea to eliminate the possibility of grounds or opens first. After these possibilities have been eliminated, it's generally safe to assume that the problem is a short. In most cases, when a short exists in the stator of a three-phase motor, the motor has to be rewound. Take a moment now to check your knowledge of how a stator can be tested. This part looks at how two types of rotors can be tested, the wound rotor and the squirrel cage rotor. If a motor has a problem and testing the motor's stator doesn't yield any answers, the next logical step is to test the rotor. The problems to look for in testing a rotor are grounds, opens, and shorts. Let's begin by looking at how a wound rotor can be tested. Let's see how a meg-ohmmeter can be used to test for grounds. The brushes are lifted out of the slip rings to separate the circuit into two parts, the rotor and the external resistances. To test the rotor, the meg-ohmmeter's ground lead is attached to the rotor shaft, and its line lead is held against one of the slip rings. Since the rotor coils of a wound rotor are connected together, the line lead has to touch only one of the slip rings to test all the coils. If no ground is present, the meg-ohmmeter will indicate infinite resistance. If a ground is present in any of the coils, the meg-ohmmeter will register less than normal, or perhaps even zero. If there is a ground in the coils, drying the motor may solve the problem. If it doesn't, the rotor will have to be removed and repaired. Now let's look at how the external resistances can be tested. The meg-ohmmeter's ground lead is attached to ground and the line lead is touched to one of the brushes. If the meg-ohmmeter indicates infinite resistance, no ground exists in the external resistances. If there is a ground, it can be located by following the wiring or by separating the circuit into small parts and testing each part. The next test we'll look at is the test for opens. A multimeter or an ohmmeter can be used to test for opens in the rotor circuit of a wound rotor motor. As with the test for grounds, the rotor and the external resistances are tested separately, so the brushes are lifted to separate the circuit into two parts. The slip rings are tested two at a time to measure the resistance through the rotor coils. The first and second slip rings are tested first, and the reading is 12 ohms. Then the first and third slip rings are tested, and the meter reads 12 ohms. And finally, the second and third slip rings, and the reading is 12 ohms. The results of the three readings should be similar. If there's an imbalance in the readings, there may be an open or a short in the rotor. To check the external resistances for opens, the tops of the brushes are tested two at a time. The normal resistance values are usually indicated in the equipment manual or drawings. All three readings should be equal. If there is an imbalance in the readings, there may be an open in the circuit. The next step would be to divide the external resistance circuit into parts and determine exactly where the open is located. The part in which the open occurred could then be repaired or replaced. If a very low reading is obtained during the test for opens in either the rotor or the external resistances, there may be a short in the circuit being tested. Also, if grounds and opens have been eliminated as possible causes of motor trouble, then it's reasonable to suspect a short. If a very low reading is obtained during the test for opens in either the rotor or the external resistances, there may be a short in the circuit being tested. Also, if grounds and opens have been eliminated as possible causes of motor trouble, then it's reasonable to suspect a short. When a short is suspected in the rotor coils, the rotor is removed and examined visually. Look for burn marks, which are a sign that a short has occurred. If you don't see any visual signs, the rotor can be placed in a growler to further test it for shorts. A growler is a device that can be used to induce an AC voltage into windings of a rotor or a stator for test purposes. The rotor is placed in the growler and a hacksaw blade, or another thin strip of steel, is moved around it. If a short is present in the rotor coils, the blade will vibrate. It's important not to touch the rotor's slip rings while the rotor is in the growler, because the voltage could cause a shock. If the rotor is too big to fit into the growler can be held against the side of the rotor. The growler and the hacksaw blade can then be moved around the rotor together to detect a short. Now, you don't have to worry about looking for shorts or grounds in the rotor of a squirrel cage rotor. The rotor bars are already intentionally shorted together by the end rings. And grounds cannot occur because the conducting bars are not insulated from the rotor. Opens, however, can occur. When a rotor bar cracks or separates from its end ring, an open occurs in the current path. A visual inspection of the rotor bars and the end rings may be all that's needed to verify an open in a squirrel cage rotor. Take some time now to check your understanding of how to test rotors. Sometimes it's necessary to disassemble a three-phase AC motor for maintenance or repairs. You may also need to disassemble a motor in order to locate a problem and correct it. In this part, we'll look at how a three-phase AC motor can be disconnected and disassembled for maintenance or repair work. The first step in disconnecting a motor is to follow approved procedures for locking out the motor from all potential energy sources. The power leads must not be touched until the power supply has been locked out and the leads grounded. Then the cover to the power leads can be removed and the power leads disconnected from the power source. Power leads are usually wrapped with insulating tape, which must be removed before the leads are unbolted. After the insulating tape is removed, the leads are unbolted. As each lead is unbolted, it's marked to identify it from the other leads. In this example, letters are used to mark it. It's very important for the leads to be marked correctly. If two of the leads are reversed during reassembly, the motor will turn in the wrong direction. And keep in mind that you may not be the one to put the leads back, so make sure that the marking is clear enough for someone else to understand. After the power leads have been disconnected and marked, the motor is disconnected from the equipment it drives. This is usually accomplished by taking apart a coupling. After the motor has been disconnected electrically and mechanically, it can be removed from its foundation and taken to the shop. When a relatively large motor is disassembled, special rigging techniques are usually needed to accomplish the disassembly. But the disassembly procedure is basically the same as it is for a relatively small motor. Now, disassembling either a wound rotor motor or a squirrel cage motor is very similar. However, with a wound rotor motor, the brushes must be removed before the end bells are removed. Let's see how a small squirrel cage motor can be disassembled. Now, disassembling either a wound rotor motor or a squirrel cage motor is very similar. However, with a wound rotor motor, the brushes must be removed before the end bells are removed. Let's see how a small squirrel cage motor can be disassembled. The first step in disassembling a three-phase motor is to prepare the work area by placing a cloth or a set of V-blocks on the bench where the rotor will be placed. The next step is to mark the end bells in the motor frame. The end bells are metal pieces that cover the end of the motor frame and support the bearings. The end bells are marked so that they can be replaced on the correct ends of the motor and lined up the way they were before the disassembly. You may hear these marks referred to as registration marks or witness marks. It's important to line up the end bells the way they were before the disassembly to prevent improper reassembly. The end bells can then be unbolted and removed from both ends of the motor. When the end bells are removed, the rotor is no longer supported by its bearings. Instead, it's supported by the stator. After the end bells have been removed, the rotor is lifted carefully out of the motor. Lift the rotor from the motor and place it on the cloth. Once the rotor has been removed, the motor is disassembled and ready for inspection. Take some time now to check your understanding of how to properly disconnect and disassemble a three-phase AC motor. This part looks at how a disconnected and disassembled three-phase AC motor can be inspected and cleaned. The inspection of a disassembled three-phase motor begins with a careful visual inspection, looking for anything out of the ordinary. For example, burn marks would indicate where high current may have caused excessive heating. If you're examining a squirrel cage motor, check the rotor for opens between the end rings and the rotor bars, and look for bent bars and for other damaged or broken parts. If the rotor is a wound rotor, check the windings for burns, which could indicate the presence of grounds, opens, or shorts. Also check the bearings. This motor has sleeve bearings. Sealed ball bearings are also commonly used. This type of bearing is checked by rotating it to make sure it turns easily and smoothly. If the bearings do not turn easily and smoothly, they must be replaced. Finally, inspect the stator. The entire stator should be checked for burn spots and loose or damaged parts. The condition of the insulation should also be checked. After the motor has been inspected, it should be cleaned. One method is to remove the loose dirt with a vacuum cleaner. Then the rotor and the stator can be further cleaned with an approved solvent. Both the stator and the rotor should be re-inspected after cleaning to detect any problems that could not have been seen because they were covered with dirt. After this step, the motor is allowed to dry completely. Then, after any necessary repairs have been made, the motor can be reassembled. Take a moment now to check your understanding of how to inspect and clean a disassembled motor. After the motor has been inspected, it should be cleaned. One method is to remove the loose dirt with a vacuum cleaner. Then the rotor and the stator can be further cleaned with an approved solvent. This part looks at how a three-phase AC motor can be properly reassembled and reconnected. The first step in reassembling a three-phase motor is to lift the rotor back into position, being careful not to drag it across the stator. Check the marks on the end bells to make sure the end bells are being replaced on the correct ends and in the positions indicated by the markings. If the end bells are not aligned properly, misalignment and binding of the bearings can result. After the end bells are replaced, they're bolted into place. At this point, the motor should be tested for grounds with a meg-ohmmeter and checked for balanced resistances with a multimeter to make sure that there are no electrical problems with the motor. After the motor has been reassembled and tested, it can be reconnected. We'll use a larger motor to see how this can be done. After the lead markings are checked, the power leads can be reconnected in the proper order and wrapped with insulating tape. The insulating tape protects the leads and also helps keep grounds from occurring. The first step in reassembling a three-phase motor is to lift the rotor back into position, being careful not to drag it across the stator. Check the marks on the end bells to make sure the end bells are being replaced on the correct ends and in the positions indicated by the markings. If the end bells are not aligned properly, misalignment and binding of the bearings can result. After the end bells are replaced, they're bolted into place. At this point, the motor should be tested for grounds with a meg-ohmmeter and checked for balanced resistances with a multimeter to make sure that there are no electrical problems with the motor. Now, before the motor is reconnected to the equipment it drives, the motor should be tested to make sure that it turns in the right direction and is operating correctly. Start the motor briefly. This is a procedure referred to as jogging the motor. If there are no problems, the motor can be reconnected to the equipment it drives and returned to service. It's also a good practice to check the current flow to each of 3 sets of coils in the motor. This can be done with an ammeter after the motor has been returned to service. Take a moment now to check your understanding of how a motor can be properly reassembled and reconnected.